Yeah, it's coming live now on YouTube.
Okay, I should just share my full desktop. It's a messy desktop, but I have also a problem, some tweaking for the MLCs for the Room B model. I'm not happy with what I've done. And I checked again with the variant, the package, the definition of the MLCs, and everything looks okay to me. But, and I will probably show you later what's the problem I'm facing. Okay, so this is my Windows. Let me get the compiled Windows. Yes, okay. So I just recompiled MMCTP, but changed because the problem, as I was explaining to Andrew, I use Slurm as a queue, and in the MMCTP application, Slurm queue is capitalized, and the script that runs it on EGS has Slurm in small letters. So I always face this problem. Let me just show you. So this is an example. Okay, so this is, for example, a beam that I have that, for a patient, and I shouldn't say the word patient, but for a plan. And when I run it, I check if the shell is online. Yes, it's online. So it's fine. It runs, no problems. But the problem I faced was in order to submit a job for a calculation, you take this thing, and now you will start. Now it will say created the input file and then an FTP or copying to the cluster or where you, the EGS engine, and then okay, so save to this. So now it's uploading the file, and meanwhile I'm going to also open the shell so we see what's the problem. Okay, so it stopped actually, and this is the problem. So the file, this script in EGS, it's actually in small letters. So I think if I went and copied or renamed that file to a small letter, then it will, it's actually in small letters in the EGS engine, but MMCTP submits it using a capitalized letters, and that's why it does not run. So the code where the EXB, it should be, we should have the EXB command somewhere here. I forgot. Here it is. This is it. So let's open Putty. And okay. So now if I actually, let's go to the DOSXYZ directory. So this is the command. I'm just copying it directly to DOSXYZ and launching it from there. And this is the problem, is that the slurm is capital. But if this is changed to small, then you see it submits to the queue. So this is something easily could be fixed. I think Andrew could fix this with the next release of MMCTP, I think. I think I've copied a compiled version. Let me check it. I need to copy this folder. Okay. So let's see if that fixes the problem. Do it again. Okay, there I see. Bilal, you can take care of these questions. Just let me finish this point and then Andrew can address these questions.
Sure, no problem. I answered some of them, which is basic.
Okay, but then we can demonstrate
things,
it. I mean, if there is something we can demonstrate, we can demonstrate.
Sure. Okay.
And if my version fails, Andrew, do you have a working version in front of you?
Yeah, I do. Yeah.
Okay, then you can actually demonstrate these questions.
Okay.
Okay, so let's try this again. So I will go now and let's do this other beam. Okay, everything fine. Everything is fine. Okay, let's change this to 68. It takes 37 minutes. Is that something good, Andrew? Or
Well,
it's a VMAT plan. It's a VMAT. It's an ARC.
That's pretty good.
Okay. Yeah. Okay, so now let's see if I'm going to have the same problem.
Yeah, you will have the same problem. I can show you where in the code the changes should be made.
I changed it, and it works on the Mac. It works on the Mac version.
Okay.
And I compiled it, but let's see now. But I want to see if it works with the Windows version. Okay, still having the same problem.
Yeah.
Yeah, so it's the same, but for the Mac version, it works. Okay, I'm gonna go back to the Mac version so that we can answer these questions Yeah, because all what I've done is in the code, I just search for the word slab and just put it as small letters, and that's it. Yeah, so, and it worked. You could also force it. You could, I mean, with Zojo, you can have use a lowercase always. Force whatever text comes from there when it's submitted to be a lowercase. Okay. So, okay, I'm done. So if you want to address these questions, please go ahead, Bilal.
Okay, so
Or Andrew, do you prefer to show it from your terminal?
Oh, not yet. Let's
Okay.
do the questions first, and then I have other things to show.
Okay.
Okay, so someone was asking how can I get the DICOM files, and it was straightforward. You just need to export it from your TBS, and you can get the DICOM RT, and then you can import it into the MMCTB. And
So what you need to export,
yeah,
DICOM RT, you need to export the images, of course.
yeah, sure.
And what else? The dose, probably.
Yeah, if you export the whole patient, you will get
Yes.
the DICOM RT, which is the plan, contains the plan and structure set and image. So all of them will be exported with the DICOM files. And we have another question. Please, how do I get to convert city images to be used in MMCTB? And he cannot get the B-link of PSCB yet to run the shell from the MMCTB.
Okay. So that the P-link, I can actually put it, maybe I can put it in the class or the Google class to share it with everyone. But if Andrew has links for...
I do have the link. It's
okay.
now up on the GitHub page.
Okay, there you go.
Yeah.
Okay. What else? Any other questions?
Yes. Okay. Someone asked, how do I link EGSnrc to MMCTB? I think this we did already. If you would like to comment on this, Omid or Dr. Andrew, it's up to you.
Well, we did it last time. We defined, so the first step is you need to get your beam model with EGS defined and working properly. MMCTP is not yet, you don't have to, you need to have something working with EGS independently of MMCTP. So you need to have a Linac model working, compiled, works well, and that's it. Now, the next step is what we have demonstrated last time is in the configurations, these are the beam models. First, you need to define a shell to access which computer has actually all the EGS engine. Where is it installed? So we have done this last time. So this is, for example, I have my EGS Windows installed at this IP, and I need to enable SSH, and yes, SSH, that has to be enabled. And then the next, the important part is this. This is the location, the home area, where the EGSnrc folder exists in the EGS, your EGS calculation engine. Okay, so if we go to this computer, if I go there, you will find the EGS folder is under this path. Once you have that done, now under that path, you will probably have your beams, okay? And you will, at least you need your beam folder to be there. And you need to also have the DOSXYZ. So let me just exit from here. Yeah. So if I go there, there is an EGS home area. And under the EGS home area, I did not actually put all the user codes from with EGSnrc, but this is my beam through beam, a beam folder, and another one important is the DOSXYZnrc. Definitely, you need the PEGs 4 The bin that's created, that I think that's where the executables are saved, and this small for the beam NRC, which holds the spec modules for your beams. So this is done outside of MMCTP. You should have this ready prior to actually configuring or running MMCTP. So in the configuration, the beam model. So there we have, I have defined a Linac beam model and so on. That's the name, the MLC settings. We went through this, but here in the configuration, now this is the beam folder. I specifically state for this Linac, when you want to submit jobs for this Linac, you should use, or the Linac is defined under beam _ through beam. You can have multi-Linacs in your EGSnrc and multi-Linacs configured with MMCTP. Each one has its own folder. So if you watch the video we've done last time, it should be straightforward. And if there are any comments, we're happy to answer that. Okay, anything else?
That's it. We don't have any more questions.
It looks like you're not able to close that window.
Yeah, I don't know why, because I resized it, and where is the close button now?
Yeah.
So when I resize it, the close button would jump somewhere. Okay, we'll just quit. Okay. Okay, so do you want to discuss something, or should I show the problem that I faced with my beam model?
Well, what I was going to discuss today was calibration of DOSXYZ.
Okay. That's an important topic, I think.
Yeah.
Okay.
Do you want to go first?
Yes, yeah, let's do it then, because I think that's important.
Okay. I do have to apologize. My one of my teeth fell out, so I have a retainer in my mouth. And pronouncing words is very challenging. But what I'm going to show is the concept, and then we can jump back to what Wamid was going to finish up on. I'll just take the screen.
Okay.
So we first demonstrated last week how to set up your beam model with an EGSnrc Linac head calculation. Once you have that running, the next phase is to set up DOSXYZ. It's important to know how your Linac was calibrated. So in this example, let me know if this is still sharing the right screen. I think I'm going to share the other one. I think this is full screen now. So your typical calibration will be SSD of 100, and then 100 centigrade equals 100 monitor units at Dmax. Calibration could change from this, but this is just one example. So if that was the case for your machine, your DOSXYZ calibration would be as such. You would want to set up a simulation where you had an SSD of 100, and you want to pick a phantom that represents something along the lines of a water phantom 35 centimeters by 35 by 35 or something along those lines. And what you would do is look at the dose at Dmax along the central axis of the beam. In DOSXYZ, that'll give you a dose per particle value. So you have your dose per particle value, and then you convert that to dose per monitor unit. And you just invert it. Because we know at this Dmax point, 1 centigrade equals 1 monitor unit. So we're setting the value of 1 at that point. So that is your dose DOSXYZnrc value. Another way of doing this calculation, though, the challenge with binding Dmax is it's the maximum dose point in your calculation, so it can be subject to higher uncertainty. So it might be easier to run a dose calibration point at 10 centimeters just to get better, just to reduce your uncertainty in that value. And then using your PDD value of 0.67, you can convert that back to the dose per particle value at Dmax, which again is the same value as the previous slide. You invert that to give you a dose per monitor unit, and that's your DOSXYZnrc value. So this is how you calibrate a Monte Carlo simulation to give you dose per monitor unit, so that when you scale each of these simulations by the monitor units for those beams, you then have an absolute dose in centigrade. So that's really the key point there. I'm going to share something else now.
Can I ask a question, Andrew?
Yeah.
If you don't do this, would the relative dose distribution change if you have multiple fields, or it still will remain the same? Relative.
The relative is fine. Yeah.
Okay.
The relative dose distribution is fine.
Okay.
Well, yes and no. I mean, if you have equally weighted beams, your relative dose distribution is fine.
But if you have different MUs?
If you have different MUs, you'll have to use those factors to scale each dose calculation. And MMCTP will do that on its own. If you put in a value of 1 as your dose calibration point, then MMCTP will just use the monitor units and that factor of 1 to scale each beam. So
Okay.
you'll have the relative dose distribution preserved. Does that answer your question?
Yes, it does. Yeah.
Okay. So one of the things I like to do is run very specific calculations for these simulations. And I'm going to show you what that means. So I'm using a non-CT phantom. And I can define the phantom within this window. And I've identified this phantom as an output phantom. And I'll show you in a bit what that means. But we have two medias for this phantom, air and water. And then if you look in the Z direction, which will be depth, there's 3 voxels. And the middle point is at exactly 10 centimeters in depth with a width of 5 millimeters. Yeah, so the maximum, this phantom is basically a 40 centimeter deep phantom. You can see that with this number here. And there's 1 small voxel and all the other voxels are fairly large. And in X and Y, it's a 40 by 40 phantom. And we have 5 millimeters along the central axis. So I've defined basically a 0.5 centimeter voxel at the location where I'm interested in. And this calculation will run. And when it finishes running, if I convert 3D dose to MMCTP, it'll add a value to an output table. If I go to commissioning data, and I go to the output table, and I click on this value, it's incorporated that new simulation. It's a 10 by 10 field. So this is the dose per particle at that point with its associated uncertainty. So that's typically how I would calibrate a new beam model. And another thing you can do is run PDDs too, if you want. So instead of having an output phantom, I just have a phantom in Z direction. And I specify the voxel size in Z and the total number of voxels. So that'll give me a 40 centimeter deep PDD, and X and Y is similar to last time, 5 millimeter width. And when I convert that to 3D dose MMCTP, I'll get a profile, and that profile is here, and it is actually quite noisy. That's not the right one. It's still not the right one. There's a few profiles here which look quite noisy, but it's a way of generating very specific simulations to pull out the data that you'd like. Other ways of doing that would be generating the full half centimeter voxel calculation within MMCTP and then drawing a line through something like these rulers where you can calculate profiles and PDDs. But there's a little bit more uncertainty here because you're interpolating values. You're not picking out the exact coordinate along, let's say, a profile at depth or a PDD along the central axis. So that was just an overview of the calibration process. And I think somebody had a question on how you convert the CT data to EGSvant information. And I can go over that too. So I'll open up an actual patient for like an actual case. This is just a water phantom, so there's no CT data associated to it. While this opens, was there any questions?
I don't see any questions here up to now. If someone would like to ask directly Dr. Andrew, he could speak it out.
You have something in your those XYZ options is MU backscatter factor or something like this. Default
Yes.
is 102. What does that have to do with the output? Or if you generate your output table, then you don't need this value.
Well, that's a good question. The backscatter factor, there's a publication, and let me just try and load up the code. I don't have a reference in the code, but there is a publication in either PMB or MedPhys that is an empirical formula that will scale the output by the jaw setting. So it's an effort to model the backscatter into the monitor unit chamber. It's not, what I've found is it's not, I haven't used it because I haven't actually validated to see if it's correct for my simulations.
Okay.
But there is an empirical formula, and I'm trying to find it right now in the code. But my quick search didn't bring it up. Just a minute, let me try again. Okay. So I'm going to share the code. Yes, here it is. Okay, I think you can see the code now.
Yes.
Okay. So this is a publication in 2000. And what it's doing is it's looking at the field size, X and Y, And then it's calculating a backscatter factor based on those X and Y positions for each jaw. And then those factors go through another calculation to give you a scaling.
And was it found to be energy independent, or so? For
Yeah.
example, would that work for 6MV and 18, or not?
It's this. I suspect there is an energy dependency.
Okay.
I bet you this is more or less modeled for 6MV. We would have to go back to this publication to definitively say how well this model works for both low energy photons like 6MV and your high energy 15 or 18MV Linac. This was a method to try and incorporate a further correction on the absolute dose for calculations. Now, whether or not it's completely valid is debatable. And the other way of doing this would be to actually look at how dose in your monitor chamber changes with field size, and then incorporate that within your Monte Carlo simulation. It's a little bit more complicated to do it that way, but that's other groups have proposed that that is the best way to correct for this effect, and the effect, I believe, is on the order of 1%. So if you're trying to figure out why there's discrepancies on the order of 1 to 2%, the backscatter factor may be the source of your uncertainty, and it is something to look into. Okay, so going back to the CT curve. So before you make a model of your CT data into an EGSFANT file, there's another configuration to do, which is CT models. This is a generic ramp to use. So it's going to use 4 materials: air, lung, tissue, and bone, based on these ranges. So you first have to set up one of these models, and you can add a model right here. And there's a number of models that I've defined. So if we keep with this McGill 521, we can then go to DOSXYZ. This is where you would generate a new EGSFANT file. And here there's a number of settings to go over. So the first page allows you to override different structures to specific materials and specific densities. Down here, this is the clean external contour option. This is saying everything outside of the body we want to set to a specific material. And there's a pull down option that you can choose. And this is a density value that you can override that to. Now for what I'm going to do is I'm going to change the CT setting to that McGill 521. And I'll also change the air. The air right now is defaulted to air 700. So I'll want to put that to air 521. Over here, this window tells you how many materials are going to be defined in your EGSFANT file. So if I had left this as air 700, I'm now going to have 2 air materials within this phantom. And this is a problem because normally you would have 521 pegs file would be one pegs file that defines materials at that 521 energy range, and your 700 energy range would be a different pegs file. So you wouldn't want to be in that situation. So I'll put it back to 521 so that everything in this material list is defined within one BEGS file. Now you have the option of changing your limits in X, Y, and Z. And if you hover over your phantom, you can see the boundaries. So let's just say we wanted to limit this a little bit. We don't need, I guess I have to go higher. So we didn't need so much data. So I can change this to the border that I'm interested in. So maybe for the purpose of this example, I'm just going to make it this large, and I'm going to shrink X and Y as well. So I can see if I'm within this box, and it looks like I'm mostly within this box. And then I can change the resolution too. So for the purpose of this example, I'll go a little bit higher in resolution. I'm going to change the name, 5mm, 4 materials. And this is going to be heterogeneity corrected because we are using that ramp. So this window I skipped over. This window is telling you how many voxels are in each direction. And you can manually assign these voxels too if you were to choose to. So in X, we have 60 voxels. In Y, we'll have 52. In Z, we have 36. I could manually make all of those voxels some material and some density if I wanted to, but I actually don't want to do that. So I want to use the CT contours and the CT data. I don't want to manually assign them. So I reselected this autofill option. Okay, so now we'll hit generate.
Quick question about the manual setting. Does it go sequentially line over line and fills the material like
Yeah,
how it's done in okay.
So it didn't like that I had entered in a material with a that it didn't recognize. So I'm going to have to kill this. That's unfortunate. Yeah, I would use that option if I was creating a water phantom. And I wanted all of the voxels to be that exact same density.
Someone wants to ask, so Bilal, go ahead, because I have some other questions. So let's give chance for others.
Oles Sao, can you please speak out? I don't know how to pronounce your name, sorry.
Okay, thank you so much. My name is Awe.
Okay.
And thank you, Dr. Wamid and Dr. Andrew. As I said, I am a PhD student, and I'm trying to see how I can be able to use MMPC-TP for dose planning and dose optimization. And my challenge is I can meet with the consultant at the hospital to get the CT images. But how to copy the CT images out for me to be able to convert it to DICOM file? I'm still not, because if I ask him, I want to get the CT images, he can release it to me. But how he will copy it out, I've asked him severally, he does not really know what to do on it. And also, I'm very, very new in this, if not for Dr. Wamid and what we have been doing on this platform. I knew very, very little about this Monte Carlo system. I did my MSc on CT scan, that's thyroid dose and risk assessment during a CT scan. So I want to continue in this field to be able to use Monte Carlos to do dose planning and optimization. And I will appreciate if I can get textbook or material for me to have a fundamental knowledge on all this, because my supervisor does not, if our own field majorly is on the maybe radiation aspect, but I am more focused on the CT scan based on my lecturing work and then the school where I lecture. Thank you.
Bilal, do you want to comment on that? I feel you have something to say.
Regarding the export, it's straightforward. You just need the to define the DICOM export media in your TBS, and you select the beam properties. Make sure that you select also the structure set, monitor units, and also the imaging. Then it will be exported for you. You will have 3 types of DICOM. You have DICOM RS for structure, DICOM IMG for the imaging, and DICOM plan for the plan, plus the DICOM dose. So that's it on your system. That's all what you have to do. You have all this exported for you as a DICOM file, and then you go to the MCCTB, and then you can import it.
I have a question for you, Awi. From where do you export your images? From the CT or from a material planning system? I don't know if he heard my question.
Okay, I've had your question. I did not. I just unmute my mic. You know.
Okay.
When I did my MSc, there is a machine that we use for the CT scan, and after the CT scan, I know that all the images are saved on the machine. And when I asked the consultant, he said if I need the images, that he can give those images to me, but where to copy it from or where to export it from, he does not, because he's a radiologist, and I am a physics person. So I want to use this for those because during the thyroid dose and risk assessment, we discovered that there are some there is need for optimization for the dose that are being given to patients. Though I want to see if it is possible for us to use Monte Carlos to be able to do proper dose planning for the patient.
This is, you're talking about CT, a dose from CT.
Yes, CT.
Okay, okay.
Would this be a system? Yeah. Like, you know, the architecture of how the images are stored? Is it on PACS or some imaging server?
They have imaging server where they store the scan after the scan.
So if a patient comes, for example, and wants a copy of their images, how does he get it? How does the patient get the copy?
What they do is that after the CT scan, they put it on a CD and they print out some things, and then
who puts it on a CD? On a CD?
The radiologist.
Okay, you go to the radiologist, okay, and you tell him, I want exactly a CD with those images. Those are probably DICOM. If he's a technician, ask them not to do any compression. So because sometimes some software, they will compress the DICOM files.
You need to have it in Little Indian format, not in ISO format.
You need to have it in
Little Indian format.
Okay.
It's called Little Indian format, not ISO format.
Okay.
Because I'm not sure if MCTB is capable of importing DICOM in ISO format. But the Little Indian is very well known throughout all the treatment planning systems, including the Eclipse, Monaco, and other systems. So it's easily to import these into the system.
Okay. The other question, Dr. Wamid, the code you did some you enter some code on EGS for us to be able to link the EGS with MMCTP. Those code, I try to enter the code and is giving me error. I think something like a bash and something for us to be able to, you did it before we start this MMCTP. That, okay, this is what we need to do. And then so I've tried to enter those code and it's not going. And I will appreciate if I can get books or materials at least to assist me in my proposal writing. Thank you, sir.
Any comment, Andrew?
Yeah.
Okay.
Any other questions, Bilal?
Yeah, we have
Who wants to
from
grab the phone?
Godwin, please, you can speak.
Can you hear me? Hello?
Yes, yes, Godwin, go ahead.
Okay. Yeah. My question is, in our center, we used to have a radiotherapy, an elector machine that has packed up. And also the TPS that we normally use in planning the patients is also faulty. So assuming I want to get the DICOM images or the plans, how do we are able to get it without the software, the TPS software running? Is there a way I can go around it, maybe connecting the hard disks to another system to extract them and still get them intact?
Okay, usually, I think each planning system has its own way for storing the images, storing the dose, storing the plan. They have their own sort of formats in their database. But you should, all of them agree that when you export, let's agree and unify this into one single format, DICOM RT. And there should be, if your software, especially if it's an old, very old one, probably you will not find that option. But if it's not that old, you should be able to export plan, CT, contours with this. You should be able to export it. What's the treatment planning system?
It's Pinnacle.
Pinnacle.
No, Precise Plan. Precise Plan.
Okay, I don't know if I have no experience. I don't know if anyone has used that.
Besides, it works. You can export as a DICOM.
Yeah, to export the DICOM file.
Yeah.
Yeah, DICOM RT. You should export like the images, the dose, the plan, the structures, 4 things.
You have to make, once you export in the Precise, you have to make sure that you tick all parameters, because you will have like checkbox for RT structure, plan, dose, and so on. So make sure that all of these are ticked out. Otherwise, the system will export only one type for you. It will be maybe DICOM image, only an image, or maybe DICOM plan without, or the structure itself. So you have to make sure that you select all of these parameters before you do the export.
Okay. But in a situation whereby, like it is now, that the system is like retrospective, I can't get access to that if the planner didn't do that.
Well, if you open the application and you can get access to the treatment planning system, try to find an option to export, and you can get plans that are, old, and export that. By the way, do you have your Linac commission in EGS?
What on EGS?
So do you have your Electa model, the Linac itself?
No.
Okay,
what I commissioned on MMCTP.
But the point is, why do you cannot commission MCTP if you don't have your Linac commissioned on EGS?
Okay.
The first step is you need to commission your Linac. Go and see the model of your machine, Electa machine. We try to make the use beam GUI, define the spec modules, define your Linac, because MMCT will use that. Otherwise, it's just an application to view, for example, those distributions, but it cannot then run calculations or do the calculations for you.
Yes, I'm already working on that.
Yeah.
I already have the geometry. I'm building the beam already.
Okay.
Yeah. Thank you.
Okay, I'm gonna continue. I hope this time it'll generate the expand file properly. So I've reconfigured the same settings as we had before. And then you hit generate. And over in this little corner, it's assigning the voxels, and it's finished.
And that's
So
quick.
once it's finished, you can view your expand file. And this is coarse because we used 5mm. So the XY direction is the XY direction in DOSXYZ. So there's in brackets, it tells you which plane that is within MMCTP. There is a coordinate conversion in this phase. So axial is this XY, or it seems to be frozen. Okay. This is the axial direction in X and Z. So you can scroll through, and using your mouse, you can see how the Hounsfield units have been converted to density. And there's a material identification for each voxel. And if you want to look at the material maps, you can change the view to just look at materials. So if we go down to the lung, we'll see that this is all lung material mixed in with some low density tissue, and then bones and tissue.
Your image is inverted, right?
It is, yeah. So the way the calculations work is this is the coordinate system for DOSXYZ now. We're looking at a raw EGSFAN file, which is an inverted coordinate system from MMCTP. Yeah, so that's how you can create your models from your CT data. And now you're at the point where you can do dose calculations on those models. So I think that completes what I wanted to show today, Wamid. I don't have any simulations running to show how it all.
I really want your help on. You showed something very nice about the commissioning, about setting just a commissioning simulation. How do you generate a physics box? Because I've been struggling with this.
Yeah. So I haven't generated one in a while, but I use the utility under transfer patient or import patient. And then under physics,
because probably this would be the next step after one has defined the beam models in MMCTP and configured them. You want to nail down that mu to particle, dose per particle conversion factor.
Yeah, you do. That's correct. So I'm having a hard time actually right now. I don't know if it's because I'm sharing my screen. It's not allowing me to click on these boxes. But what I've done in the past is I've created those physics boxes.
Okay, can I share mine so we can demonstrate it on what I have?
Sure,
okay.
Yeah.
Okay, so this is the transfer patient window. So we'll click on physics, and then, so I'll call this, physics box, fine. Okay, help from Andrew. Don't like spaces.
No.
Okay, from Andrew. Okay, let's see if it will work. And then the image size. What I usually do, I will use the 512, but probably it's not important if I'm doing this commissioning part. I don't need this number of voxels probably. 40. So in the Z array, so these are the number of slices. I would say I'll use 80. And here, let's say 80, 80. So in that, I'm thinking of a 40 by 40 by 40 centimeter phantom with 5 millimeter voxel size.
Okay.
That looks okay.
You would have to change those three numbers, the 1 and
yeah. But I'm just thinking about the number of voxels. So yeah, this is 5, 0, 5. Okay, and this is the because now we have a cube. So the coordinate of the first cube, this means that the 0, 0, 0 is at the middle of the phantom now.
Yes. Yeah.
Okay. So fine, answer unit. Okay. Value. Okay. I'm going to use a uniform CT number. I want everything to be water. So the CT number is 0 for water. Okay. And this is the one. Okay, so now I'll close this and we will open hold on, where is it? And now we'll open the patient. So this is the new patient. CT, open. 40 images, that's the 40 slices. Okay. Then, okay, because I don't, it doesn't have a CT number, or, you know, it's, I get black. So usually what I do next is I would actually add a beam. Okay, and define. Okay, I have one photon, 2 beam rows, and this is fine. Okay, the geometry, 10 by 10. And accessories, MLC is static, that is fine. So I guess I'm set now. And just to prove it, okay, let's do one more thing. I don't want, because it's 100 SSD. This is, we calibrate the beams like what you have shown, Andrew.
Yeah.
So probably I need to change the Y here, this to be minus 20.
Yes.
Right. Is this clear? Is this clear to everyone? Because the 0, 0, 0 coordinate is in the middle of the phantom, but I want the center to be at the surface of the phantom. So we have 100 SSD. So I'm changing the isocenter location within the phantom to be at the surface. And okay, so now, so just to, I mean, this should work because this is the beam simulation. But the dose simulation, that's really the important one. Okay. So now the dose XYZ simulation, this is where I struggle.
Okay.
Okay. So okay, if I look at the phantom, I'll show you what's my concern. Okay, view X phantom. Okay, this is a problem I face. Now the phantom is air. Everything here, the density, if you look at the density, it is air. And by material, it is air. Okay.
Okay.
That has to change to water. How do I do this?
Well, let me see how you created the phantom. So
should I go back? Okay. Should I delete these?
Probably. Let's leave them there, and we can figure out what went wrong with them.
Okay.
Or you can delete them now because we know they're wrong. It's up to you.
So delete, because by default it generates. But let's delete them.
So one thing you can do, Wamid, before we get too far, I would go to View, go to your View options. Can you change the window width or the level so that you get some contrast?
Here, the level, it's 0. Okay. Yeah, there it is. Okay.
Okay, so now you can see the borders of your water phantom. And if you use your mouse and you scroll over that, what pixel value?
0.
Pixel value is 0. So that tells me that something has gone right. You have something that makes sense.
Okay.
So now we can go to DOSXYZ.
Okay, and generate the phantom.
Generate the phantom.
So just for everyone to understand what this is an image, like a patient, but those XYZ calculation, we convert the image into voxels, with each voxel has a given material. So this is what we want to do now. That's called EGSnrc file. Okay. Fine, this is okay. I could use another thing. Now the voxels I have, remember, for the phantom were 80.
Well, for this one, it wasn't. This was created, you created this beforehand. And of whatever reason, this one has 130. Well, this, if you go back to your MMCTP, you can see the dimensions. And it's not 80. It's actually 40 in Z, 512 in X, and 512 in Y.
Okay, here it is. Yes, this is 20. So this is about 20. Yes, 512. I see now your point, the resolution. Yes. Okay, so what
but
did
we can work with that. This one you created offline.
Okay.
I would just work with it in the next step.
So generate the new X phantom.
Yeah.
Okay. So here, then I have, so I can assign it manually, right?
Yes, but you'll want to, if you go over to the EGSnrc tab, the last one, you'll first want to set your resolution in, if you want 0.5 centimeter voxels, or if you want 3 millimeter voxels. Right now you have 3 millimeters. You can leave those as default.
Well, let's make the numbers, minus 20, okay. Minus 20, 20. Okay, and then this is 5, 5. Okay. And generate?
No. You'll want to go to manual.
So no non-CT phantom, right?
No, incorrect.
Sorry. Sorry.
The non-CTV phantom is for the commissioning phantom that I was talking about.
But this is exactly what I want, Andrew. I want to get an output.
You still will with this, but
okay.
The non-CT phantom will not use the images that you've imported into that patient.
Okay.
You're still using these images, even though they're virtualized fake images. You'll still want to use them, I believe, for your purpose.
So here, should I change these to now to match the number of voxels so that everything is replaced with the, or it will override, it will use this new.
It's using that information. It's using those EGSnrc EGSfant limits to determine how many voxels you have. And that's why it's saying 80, 80, and 80.
Okay, so here, so from X1 to X, and here this should be 80.
Well, let's go back. I think you made a mistake in Y. So Y you have going from -20 to positive -20.
Okay.
So then you can go back, and now it should say.
Okay. Now I'm starting to understand how this. Okay, and the material. Just for your information, I keep actually 2 copies in my PEX data file. I keep a 512, 521, and the 700 versions, so that I can use, like in the case where if air outside of the patient, I can use the 700 because it's faster.
Right.
And,
That makes
and
sense.
yeah.
Yeah.
So I have both actually. I always do this when I create any PICS data file. I would actually create both.
That's smart.
Yeah.
So you want to create a medium outside your Phantom too. You'll want to assign that.
So now I can put 700 IC area. Okay. I do have in the file Air 521, but
Okay. Yeah,
I'm going
that
to
makes
use
sense. What you're doing.
Yeah. Okay. And then go back to here, this tab.
Okay. Well, we have it looks like there's actually a
Something
problem.
missing, right?
Yeah. Maybe hit tab or enter. It should be identifying that as a medium. Or go back to contour settings.
There is nothing.
What you can do, Wamid, is go back to your CT settings as well.
Now it is
Oh,
there.
it's finally figured it out. Okay.
Yeah. Okay. So I put 5 millimeter and no for water, just so that.
Yeah, 5 millimeter water. That sounds good.
Okay, and hit on generate.
Yes.
Okay.
So now when you view it, I think it'll look good.
So we have water. Okay. Voxels not loaded. And let's look at material.
Okay, it says the XFANT voxels are not loaded.
Okay.
What that means is you'll have to close this. It normally loads the voxels when you open the patient, but when you create a new XFANT file, all of those voxels are already loaded in memory. So I'm a little bit curious as to why it doesn't see that already. There's an option. You can go back into it again and confirm.
View.
Yeah.
Okay.
Yeah, you're not loading the images. So what we can do here, so all you'll able to see without the images is the header information of your XFAN file. But there's another option within File, DOSXYZ. You have to go to the File menu.
File menu, okay.
Yeah.
Image information or
configurations, DOSXYZ settings. Now, when you load a patient, you may not always want to load the voxels. So you have the load XFANT voxels selected when it opens.
Okay.
So you should leave that on, but this is just to let other people know that if that's turned off, MMCTP won't read in the XFANT file every time your patient opens, and it saves some time. But we want to see that. So what I would suggest you do is you close the patient and open it again.
Okay.
And it'll read that file when the patient opens.
Just confirm, yes, okay. So let's close, let's save, and let's open.
So when you go to the DOSXYZ tab, it'll show the progress of reading each XFANT file.
Yeah, assigning voxel values. Okay, but this is okay. Yeah, because there is an auto generate, that's why this one is already generated.
Okay.
So view. Okay, now it works. Now the density is 1 here. Okay, and if I look at the materials, then the color matches. So water and water. So now
Okay.
it works. Okay. And just so you know, Andrew, I always use the treatment head simulation. I don't deal with the text data files.
Okay. Another thing you can do once you've launched the simulation.
By the way, just so that everyone understands what I was talking about, the MU backscatter factor correction is this thing here. Okay, that's what Andrew was trying to explain. Yes, go ahead.
One thing you can do, Hamid, is are you going to submit this job or do a test run?
Yeah.
Okay. We can go back to the images and look at where your ISO center is. There's a little dot that will display where that location is.
So I can launch the job and then we will go to the images. Okay. So now it did a simulation run, just about 2,000 histories, and estimated it needs about 4.7 million histories to get the uncertainties. I think this is at Dmax or at maximum dose value, this uncertainty.
That's a great question, actually, Wamid. If you scroll up from the text on your right, you'll see an average uncertainty. Keep going a little bit up further.
Okay.
Keep going up. There, right there. This page shows you, oh, I think you passed it. Did you? Yeah, go back up. Or is it down?
Scroll down here, right? This is, no, that's the had an uncertainty.
Here you go. Here you are. You're there.
There it is, right?
Okay. So it's reading this number on the lower left, average percent error of doses greater than 0.5% of maximum dose equals 48%. And you see where that line is coming from, the simulation.
Okay.
So it's the average error of the 20, no, it's exactly what you've highlighted.
Yes. Okay.
Yeah.
So in order to get estimation to get this value 1%, then it needs to run about 4.6. You can override this and add like put 5 million or 10 million. And the number of jobs, this is what I like. So this in 7 minutes I should get this done. And we will leave this for the time being. So now we'll hit close. And then I'm going to click on this, and now it's creating it, uploading, and I should start to see my queue being populated. So there it is. Okay, so now we can do the view.
Right. So what I would do, I go to view. And,
you know, I have a problem with there is a problem with the Mac version.
Yeah, there is. Yeah, I haven't figured out how to fix that one. Uh-oh, you've done it now.
Yes, okay, this one.
Okay, there we go. I would scale down the top. Right now, your top is 100%. There's a little slide bar lower left. Scale that down to maybe 80% or something, or 60, just so that we can see the whole thing. And now you'll want to show ISO center. And now if you click on your beam, you have to go to external beam, because you can have ISO centers for each different beam.
There it is. I see it now.
And there it is. So I'm very confident that you have that set up at SSD 100 now.
Yeah. Okay.
And the other way to verify that is to go to your DOSXYZ settings. And then click on that beam.
Okay.
Go into advanced. And go into source 10.
Source 10. Okay.
If you go into source 10, it's going to show you the distance from source to ISO center is 30 centimeters.
Yeah.
So if your beam simulation ends and you know it ends at 70 centimeters, now you know that your DOSXYZ simulation is going to start at 30 centimeters. That gives you 100 centimeters to your ISO center.
Yeah. But this value is fixed, Andrew.
It's
Will
not.
show up. It will show up even if your center is in the phantom, because
Oh,
it's just
true.
it's a distance from the phase space, or what's supposed to be the phase space, to the isocenter.
Yes.
Yeah. Okay.
Yes.
Well, now I'm getting to play with these visual things, because I could not figure out. Is there a way to show, for example, a projection of the fields, or it does not have that feature?
Currently, there's no option for that. No.
Okay.
There used to be. A long time ago, Zojo had a 3D viewer that allowed us to visualize the fields on the patient. But that module was basically decommissioned, and now it would have to be recoded in another 3D viewer that Zojo has chosen to move forward with.
So here it's showing the progress of the calculation. So now we're about 28% done. Okay. What other features here? This is the crosshair. What does that represent?
That shows you where you're looking in the different
Okay.
plane. Well, actually, crosshair is nothing. Sorry.
Yeah. Okay. And the mouse crosshair.
Mouse crosshair is just where your mouse is. The other crosshair shows you the sagittal and coronal slices. So if you were to
okay, if I had some, this works.
If you had something other than a box, you might see something different. But
okay, let's try this. Yeah, of course, in a box it will not. I will not see anything.
Yeah.
Okay. And what about the axis?
So if you take off the, if you go back to the axial one, the axial image, you'll see your coordinate of first point, and then it's just a ruler from there on.
Okay.
So that crosshair where those two coordinates meet is the border.
Okay. So the crosshair is for the images, how they translate from one view to another.
Yes.
How do you actually? I can't, for example, go to other images, other slides.
Other axial slices? Is that what you're asking for?
You can do this in Windows. Do you press on a button?
It should just be the arrow key.
Arrow. Okay. So, okay, it does not work on my Mac.
Up, down. Up, down.
It's a box. I cannot see it, but maybe I can open a patient. But I saw it working on your Windows version anyway.
Yeah.
And on the Windows version, the DVH still does not work. The one that I've downloaded from your site, from GitHub. For some reason, the DVH still did not work with me.
It's not launching the calculations. Yeah, we saw that.
Yes. Yeah.
I do have an old Mac. I can look at updating it to the new version. Which Mac OS are you running?
Well, I'm using Catalina, right?
So
with Catalina, things have changed because of just so that you're aware of this. This is also something you might consider changing. Where is the app? It's okay. So here, I think this is where you set your methods. I forgot where it is. This is where you remember where you set the default folders.
Yes.
Now things for the Mac it does not work. The special folder application is not good.
Oh, okay, I know what you mean.
Yeah, so you have to fix that. I fixed it, and everyone is they're not happy about it. The Zojo community with how a Mac. So MMCTP. I think if I search for
Yeah.
MCTP folder, yes, this is a special folder. It doesn't work with Catalina. It works with previous versions of Mac, so it has to be changed.
I see. Yeah.
Okay. Okay, so, and I will need a session how to actually, because there are a few modifications that I've done, but I don't know how to actually put them into the GitHub, for you to review. So that probably in another session you can show us how to do that.
Okay. We can go over that next week. I actually had some submissions to upload in the past 2 days as well.
Okay.
And one of them was probably an error that we ran into last week, which was a space within the local path folder. I attributed that space to why we weren't able to transfer some files on your computer. And when we moved everything to the C drive, then the Windows transfer function was functional once again. So now
I would also try to compile it for an ARM version,
Okay.
just for fun.
Yeah.
Okay, so we're almost done. So now all the jobs have completed, have finished. Now when it's done, you should see this message about to download the 3D DOS file. It reads the date, it reads the uncertainties, and then we should find here. That's the DOS file. And if I hit on view the color wash, there it is. Okay. So what I usually do, if I want, just for fun, okay, let's put this at minus, this is 0, I believe 0 and minus 20, 0. And then here we have 0, 20, 0. So I'm setting the 2 points where I want the profile, to get the profile. This should give me a PDD. And when I do a calculation, and then I select the dose profile, show. So on the y-axis, this is the PDD. What I was doing, Andrew, was getting the maximum value. So maybe this could be used, like the way to commission. I know the maximum along the PDD, central axis PDD. Then I will. But now the question I have is, okay, this is 5.95 10 to the power minus 12. Where do I put this? So here in the dose calculation.
So I'll show you. Yeah, you put that.
Or I put the reciprocal of it.
Yes.
So I need the reciprocal?
Yes. And if you want to assign it permanently for all future calculations, it goes in a settings file. But if you want to just change this calculation, you would do it right there.
So 5.95e minus 12.
Yeah.
So that's the value I should put.
Yeah, that's the value that'll give you 1 monitor unit equals 1 centigrade at that point.
Scientific. So 1.68 10 to the power 12. Okay. So 1.68 is the power, is it 12 or 11? I forgot the value. Okay. Okay. By the way, that is for gray or centigrade, just so that I'm not confused. It's a conversion. Those to water. This one, this is centigrade.
Yeah, that dose to water factor is more or less ignorable. That's if you wanted to convert your dose to medium to dose to water.
Okay, okay.
And there you would have a specific factor that's close to 1 that the user
Okay.
would enter in.
Okay. Okay, so if I want to change this permanently, probably we need to somewhere here in the configuration. Those XYZ probably.
So in beam models.
And the beam models, yes.
It's
Okay.
associated to your Linac.
Yes. Okay, so it's here.
It's right there.
Okay.
I'm going to warn you though, the number that you're entering may be off by 100 because.
Fine, but it's just because if I'm doing this simulation properly, I would just go and like do 10 like a lot of more particles.
Right. Right.
Yeah, but yeah, okay.
Where I'm saying, Wamid, is if you were to close, you can enter the number in here and close this.
Okay, let me just.
The profile, the dose that you've just imported has already been normalized by the monitor units for that simulation. So if you go back to external beams, no, just the tab down here.
Just a minute. Let me put the value 1.68. 68 e to the power 11. Okay, so that's the value.
Well, what I'm saying, Wamid, is that is probably off because if you go to external beams, the tab here, you probably have set 100 monitor units on that calculation.
Okay.
So that calibration is now going to be incorrect by 100 because you want to set this to 1 monitor unit.
And run the simulation.
Yeah. Well, no, you just have to renormalize the dose. The simulation is what it is, but when you convert that 3D dose to MMCTP, it uses the monitor units to scale all of those values. So
I don't need to run a simulation. I can just click on 3D dose to MMCTP again.
That's correct. Yeah.
Okay. These are features I was not aware of. Okay. And then the dose profiles. And then if I select this and you hit on calculate. Okay, I think the problem because it actually got the default value that I've entered, and now it's sort of multiplying it twice or doing it twice.
Well, let's see what it's doing. It's the max value is.
Yeah, this doesn't make sense. It should get 1, right? Or if, but I think it already.
Yeah, I see what you mean.
Yeah. Anyway, this is something I will look into, and the last point is how did you remember you added something to the commissioning?
Oh, today you mean?
Yes, today. So you had like a commissioning table for outputs, and you were assigning values. This cannot be done with this phantom. I have to do a.
You would have to create a commissioning phantom.
So, okay.
Yeah.
Okay.
That's where you generate new phantom.
And we'll go here. So non-CT phantom. This is, I don't need this. If I'm doing a non-CT phantom, I can here enter a different, yeah. Okay.
Well, it depends because it's still going to use some of these settings.
Okay, so you suggest I change them?
You have the option of changing them later as well, but I would.
Because I thought there you're just setting the voxels and it's.
Yeah, you're correct. You can leave these as.
Yeah, I think they're not relevant, right?
Yeah.
Yeah. These are relevant when you want to do a CT phantom, I think.
Yeah, you'll still need to. The name, I would try and define it so that you can remember what it is. So profile, that's good. Or you can specify the depth too.
Or we can just make output, right? Output.
Yeah.
Okay, 10. Let's do the 10. I like the idea of doing it at 10 cm. So non-CT phantom generate could not. Okay, I have a problem. So could not find this phantom output. So I need to actually have a phantom, a water phantom output X input file. I don't remember. I don't have a file like this.
Yeah, it's true.
Yeah.
I can we can go over this next week.
Yes, because I want things to go logical. So first thing is the configuration, and now we are doing some sort of proper commissioning, let's say because of MUs and so on. I think this is a very important step.
Yeah, I would agree. Yeah.
Yeah. And then the next step, we will do like a plan, like what you have demonstrated to us, where we can show DVHs, make two different, let's say, calculation, one just full of water and one with a different, with heterogeneity corrections, and so on.
Yeah, I think looking back on the presentation I gave, Wamid, I gave you some wrong advice as to whether or not you invert. So we'll have to revisit that as well.
Okay.
I'll
Anyone has questions for Andrew? I don't want to, you know, I want to give others. Bilal Hussein, probably you have something. You always come with a very good question every week.
Yeah, Bilal Hussein is already asking. Bilal, you can speak rather than writing, please.
The discussions today, because I really wanted to know the step by step how to create the water phantom and do this thing.
Yeah, I think this is very important. I was struggling with it personally. I managed to get DICOM files, but for those who cannot get DICOM files, you can make just a water phantom and do simulations. If you are testing, for example, a beam model, you could do it from the. You remember we were using those XYZ and then stat those to extract the profiles.
Yes.
So maybe one can do it with
Those XYZ show.
those XYZ show. Remember, those XYZ show had a problem. The problem was if you don't have uniform voxels, you run into trouble.
Yeah.
There in the display showing things. This is what the Singh actually showed us. I remember that.
I tried to actually import one of the radiation plan, but actually it was not, all the images were not getting imported. It was saying that there are some actually pixel problems.
What's the radiation planning system?
It's actually on Centra. Electors on Centra.
So you heard what Bilal said. Try to little
Yeah.
Boolean, a little Indian, right?
Yes, it is Little Indian. In fact, it is saying it is Little Indian. It is trying to import. When it was reading all the images, in between it stops suddenly.
Mm-hmm. Okay.
Maybe I'll actually export it again. Once again, I'll export and check it up.
Yeah. Okay. So I just want to, show something. I had a problem with my true beam model, and I could not figure this out. But if someone else has a question, please go ahead. So, Andrew.
Well, I just want to correct what I said, Wamid, if I can take the screen for a second.
Yeah. Take it. Okay.
Okay. So I have the code for our normalization, and I gave some bad advice in my presentation. So these three lines is how a Monte Carlo dose is normalized. So you have this normalization factor, which is the number of fractions for the beam. This is a DICOM number. Then times the monitor units for that beam. Again, you get that from your DICOM file. And then beam weight, which is another parameter that comes in through the DICOM file. Normally, beam weight would be 1. And you're really only normalizing by monitor units. So this is your first number to convert to absolute dose. Now to go for the Monte Carlo normalization, you have your dose to water value, which we briefly talked about. It's almost always 1 because we're not usually converting dose to water from a Monte Carlo simulation. And then we're dividing by this Monte Carlo normalization value. In my presentation, I thought we were multiplying. So Wamid, you don't invert.
Okay.
You just take that value straight up. That straight value that we had in the profile, you use. And in my calculations for the presentation I gave, you wouldn't invert as well because we're inverting within MMCTP, we invert that value. So this is the real line. So it's very simple. You take
That's why I was getting minus 25, 10 to the power minus 25, because it's probably inverting twice, probably.
Yes.
That's why. Okay.
That's exactly why. Yeah. Okay. Sorry about that, everyone.
No. Okay. This is Andrew. Are you familiar with? Have you done simulations with a true beam?
I have. Yeah.
Okay. Okay. I suspected I think I have a problem with the MLCs and their location, not the geometry, but where they are. Because what I've done is, this is a beam, just to show you. It's a 10 by 10 field, and MLCs are pulled out completely. And this is, I think this is the dose, this is it. Now, the first field, I did something different. I opened the geometry to 20 by 20, the jaws, but defined the field with the MLCs to be 10 by 10. So I went here and went from leaf 21, see, from leaf 21 up to leaf 40, that's 5. So that should give me a 10 by 10 field defined by the MLCs. The problem I'm facing is I ran the simulations, and this is the one with the MLCs. See, it's a bit up here. And this is the one with the jaws. And to show it better, so I can, let's try to make a, I think 0, 0, let's try this, minus 50. So 0, 0, okay, doesn't matter. This is 7, we'll put 10. Okay. Then I select the other one, and I show both. Something is not correct, and I don't know what is the issue.
We can't see the profiles right yet.
Okay, so let me change the color. So this, I'm going to make it red.
It must be on your other screen. Maybe others can see the profiles.
Oh, because I'm sharing. Okay, I should share the screen, not just the application. Okay, sorry. I'm sharing a window. Now I'm sharing the screen. Okay, this is the problem I'm facing.
Right, yeah.
Okay, And I checked it several times. I don't know why I'm getting this gap. This is about half, this is probably around 1 cm. This is 1, 2, 3, 4, 5. Yeah, this is roughly around 1 cm, I would say. And I have no explanation for this problem. What I suspected is I probably have the MLCs defined at a different source, not appropriate distance. It is off. And I've copied, or these the values I got from the through the Monte Carlo package from Varian. And I checked it twice and it's not working. So I have a problem with the geometry with MLCs. The thicknesses, because the issue, I believe, with MMCTP, regardless of where the leaves are, it's always going to correctly calculate the leaf openings. Okay, because just from geometry. But it cannot handle if my thicknesses are wrong. So if my thickness this is what I got from Varian. Let's say the leaves are 2 millimeters thick. They have to be at a specific position from the source to the isocenter. That position, depending on where that MLC is, it will change this penumbra or geometry of the field in that direction. And I think that's where I'm having the problem.
It's hard to debug these issues, but I would one thing you can use is go and look at your input file in the beam geometry tool to see if the MLCs look appropriate there.
They look appropriate. You mean in GUI or here?
In the GUI, yeah, in the beam NRC GUI.
Beam NRC GUI. I mean, that's simple. So go and open, load the previous. Okay. Oh, I don't have that file there. Okay. Anyway, I will look into it because now we're reaching almost 2 hours.
Okay.
I will look into it more. But if someone has, nailed this down, then I would really want to know where is their MLC. So here. So I tried, for example, to use, where is it? 48.175. That is distance from the source to the component module. And then I tried another one. So I'm trying to debug this to see
if we look at that profile, it looked like one side looked appropriate, and there was just a geometry offset on one side of the profile. So it's hard for me to figure out if, like, why would one side be correct and the other side be incorrect? I don't know.
Well,
okay.
Okay. You see, there is, let me open this again. This value also is not given by Varian. Where is that value? Okay, this one, the starting position of the leaf sides. You see this value, I had to calculate, I have to figure out manually. So I was adjusting it until I get the penumbra side, match.
Okay, and just for everyone's sake, when you drew that profile, are you drawing across one leaf pair? Is that what we were looking at?
It's across, no, it's actually between both banks.
So from bank A to bank B,
it's actually, no, it's between the banks. So so it's not crossing the banks, it's not from A to B, but actually the other way.
Oh, okay, so it'd be along the Y direction.
Maybe? Along the Y direction.
Okay. So then it sounds like one leaf is in when it should be out, or something along those lines, or it's the thickness, like you mentioned.
Well, you see, this distance, this thing, okay, your leaves are coming like that. We know this, okay? They're parallel, they're stacked. And this parameter defines where is the location of the first leaf from your isocenter. So I can always shift. Imagine if we go manually to the machine and we slide both banks in one direction or the other. So this is I had, this value is not there. I had to manually play with it until I could match one edge, like using this 10 by 10 geometry to match the jaws. Because I can change this value, let's say to minus 10 point, I can put it at -9, and you will see that the both profiles are completely off. Although
Okay.
in MMCTP, it looks fine because you don't have that issue.
Right. I see you now.
Okay, so I was adjusting because if suppose this is your isocenter, the distance from the I think this, I'm not sure which leaf, but the distance from the first leaf to the isocenter is this value, and I can always change it with with beam. That's not a problem. So what I've done is try to manually fix that value so that I get the edge of the 10 by 10 field on one edge to match the jaws. Then I discovered that the other leaf from the other side is quite off. This is the problem with the profile. So I suspect this value is not correct. So I think the MLCs probably are closer to the isocenter than this value. But anyway, we can look into this maybe some other time.
Yeah, we can.
Yeah, okay. Bilal Hussein, probably you're good at figuring these things out. So I hope you understood the problem I'm facing.
Yeah.
Okay, so any other questions before we conclude for today?
I don't see any questions in the chat up to now. But I like the way that we did it today. It was like troubleshooting. So the mistakes that we do, at least now we learn from it. And Andrew, you really, your existence in this group make it very easy for us. Otherwise, we struggle a lot. Because MCCTB is not easy to configure. There's a lot of things to you have to handle it. But your existence here is really very important and makes things more clear for us now.
Well, I'm happy to be here. Thanks.
Thank you very much.
And we're getting him for free. Well, I think this, Andrew, is going to encourage you more to actually, look at these bugs and frequently, or we get more frequent updates than usual.
I think so. Yeah.
Yeah. Okay, in that case, thank you very much, Andrew, for your time. And next week we will have another session to continue on this path. You can always put a link, to the videos, Andrew, from the GitHub for people to watch this. And I've seen some. I'm getting new subscribers to the channel. One thing I don't have in the channel is a link to how to register for our sessions. So probably I'm going to put actually that, so that probably we're going to get more people attending these sessions with us. Okay. Okay, then in that case, thank you all, and good night and good afternoon, Andrew. See you next week.